So, still on symmetry planes and using them to simplify the computational domain and ultimately the problem. In the previous video, we looked at just the monopole modes, the quadrupole modes, and generally um, even other modes in the azimuthal. I mean, it's derived. It's tricky to call. For m is even for your TM and OK mistake. I mean not mistake, omission. And also TE. So generally your TEM and TE MNP mode. So for the azimuthal polarization, you have M is equal to for M is even. Then we had these conditions generally applied for simplification. And what we also said was that you lose some modes, but then since they are different polarizations of exactly the same mode with the same properties, then you shouldn't lose um, information. But then always check, always check. In this video, we'll be looking at for when M is odd. So for your dipole, your sextupole, your decapole, and also the higher order modes that come. So I already copied this. So let's see, for dipole mode, I already copied this, but then I'm going to be editing them. So these, I don't think these are correct. I'm going to be editing them. So yeah. So one thing I noticed about the dipole modes that were calculated is that I remember that we are constrained to just these 4 planes. So these are orthogonal is it three planes, and now you see that the dipole mode is not oriented at 90 degrees or 180 degrees. So this poses a challenge for us to check the symmetry. But then looking at the mode itself, we could see that there's some symmetry about this axis and also there's some symmetry about this axis. So we have to determine what symmetry um, we would have to apply for these axes. So for that, instead of, so normally I would, okay, I already went ahead to do that. So normally we would check on the x on the yx plane, xz plane, and then xy plane. But now our fields are not oriented in this plane, so we have to use free. We have to rotate our fields, and yes. So I mean just an approximation because I don't know the exact angle, so I'm just going to use an approximation, and then we do wait. And then we do exactly the same thing we did for the previous one, which is check which of the tangential components on this plane is 0. So I'm going not to absolute but then to tangential. Now this is E. So we see that E tangential is 0 everywhere on this plane. So E tangential is 0, but H tangential is not 0. So that's for the first plane. Now, since we do not have corresponding orientation to YZ or XZ or anything, we're just going to go with the YZ is equal to ET. So we just take one plane. We just take one of the planes, any plane at all, like I explained also in the last video, that these are just because we just have these because of the way I modeled my geometry. So that's why we have this. So it could as well be, I mean, depending on how you model your geometry, this could as well be xz first, and then xz, this could also be xz et. So it depends on how you model your geometry, and then you have to determine the planes relative to your model. So since this does not correspond to any of those planes, I would assume that I can rotate this I can wait. I would assume that I can rotate, if I should rotate my cavity this way, then I can have the symmetry planes aligned to maybe the y if I have to use local coordinates. But then if I have to use local coordinates, I would have that this would be one, then the other symmetry plane would be at 90 degrees from it. So that's what's important for the symmetry planes. I mean, now we have 2 symmetry planes, but it's not compulsory that you always have 2 symmetry planes. You could also have 3, like we saw for the TM010 mode and the TM010 mode and also the TE010 mode. So I would have to correct all of these too. So, and also TE010 mode and then TM and then TE0N0 modes. So we had 3 symmetry planes. So it's not compulsory that you always have 2 symmetry planes. You could as well also have 1. But then for this, we see that there are 2 symmetry planes which are 90 degrees from each other. So we know that we can use either of the three planes that we have in CST. So the three planes are X, Y, Y, Z, and XZ because they are 90 degrees offset from each other. So that's what's important. So we've looked at one of these planes. Now we have to look at the other one where we see the symmetry. So I will go ahead again and have this. Then this time I would rotate it. So the way I'm rotating it is grabbing one of these. I hope this is not skewed. So I would first of all align it to the X, and then yes. So I'm just trying to get an approximate because I don't know exactly what angle this is. And then on this plane, you have that ET is not 0 because you have field values, and then HT is 0. So you have that HT is 0 on this plane. So since I choose this to be my first plane, now your XZ is 90 degrees from, your XZ is the next plane that is 90 degrees from that is 90 degrees offset from the YZ plane. So your YZ plane rotated 90 degrees, that's your XZ plane. Remember, you'd have to now rotate to get the XY, because of the way I oriented my model, to get the XY plane, you'd have to rotate it about the Z axis. So, but then rotating about the Y axis, then you'd, no, about the X, then you'd have your XZ plane. So for this, you have that H is equal to 0. Now let's look at for the last one, Ctrl Z. Let's see for the last one, 6, 9, no 6, yes. So for this, we see that there's a symmetry plane about this, or there looks to be a field symmetry about this, and this should be, I think this should be your T111 mode. If I'm not, yes, this should be your T111 mode. So there's a symmetry about this axis, so I would go ahead and get my C and then orient it with respect to Z, yes. And then look at it, so I have that the ET is not 0, but then you have that the HT. So the transverse magnetic component is tangential, not transverse, tangential magnetic component. I always mix these two words. Tangential magnetic component, not transverse, is 0 on this plane. So yes, I could apply that, but then this would only be for the T111 mode. That's where you have HT also equal to 0. But then generally for all, and then I could show that this doesn't hold for the next mode. So the next mode would be the second polarization. So the same thing should hold. So, but then if we should go to the next mode, the next dipole mode, the next dipole mode is now the T, I think this should be, wait, this is T111. I mean, I'm hoping I'm correct. I didn't mix up the mode names. So then you don't need to know the mode names, and let's see. Yes, so this should be, I think this should be TM11, let's see, 6. Um, hmm. Yeah, I would not even try to figure out the mode, but then this should also be a 1 in the Z direction, probably. Wait, or maybe it is 0. Might be a TM110 mode, but then I think for this one you also have symmetry on this axis. Now let's look at what type of symmetry it is. So look at section C, and then in this case you have that ET is not equal to 0. Wait, I'm looking at the absolute. Also be careful that you're looking at the tangential. So ET is 0 and HT is not 0. So you see that for this mode, for the T111 mode, while you have that on the XY plane, HT is equal to 0 and ET is not equal to 0. But then for the next mode, which is the TM110 mode, HT is not equal to 0 on the XY plane, but then ET is 0. So you have these two conditions for a dipole mode. If you were to use these three symmetry conditions, then you would have only modes that satisfy this, which T111 is a part of it, but then you would lose the second dipole mode. So generally, these modes, these symmetry planes apply for all dipole modes. Now let's look at, and this should also apply for sextuple modes. Let's look at one example of a sextuple mode. I think that was 18. Okay, now this might be, okay, not very difficult to check. Maybe tricky, but maybe not very difficult. So let's see, as we did before, I'm going to get, so let's start with X. So we have this, oh boy. So I'm going to get the absolute, and then you see the planes. So it's also not aligned to the X, Y, Y, Z, and XZ plane, so we have to rotate it. So I'm going to go first with this, and then I'm going to hold this knob here and then rotate it. Yes. Then I look on that plane, and then I go to the tangential component, and what do I see? I have that ht is not equal to 0 on this plane, but then you have that et is equal to 0. Now you could still see some field. But then it's because we this is because the axis is not properly aligned. If it were to be like perfectly aligned with the axis of the symmetry, then you shouldn't see any field value at all for this. Let me see if I can try to do that. 3. So it's kind of difficult to do. Let's see. Yeah, something like this. Let's look at this again. Yeah, you see that the field, there's a point where you wouldn't see a field again. So you have that the first condition is satisfied, et is equal to 0. The first symmetry plane condition is satisfied, et is equal to 0. And then for the second, let's see. So we have this symmetry which is also repeated. So this symmetry is this symmetry is this symmetry. I don't know if I can. Can I annotate this? I think I can. Yes. Yes. I've never tried this before, but I hope it works. Let's see. So, thickest. Okay, yeah, it works. So we have this, then we have this, and these are similar symmetries, right? And then maybe I can change the color. Okay, I think I have a limited. I think I have limited palette here, so I'd use the thick lines for one symmetry, and then you see that you could also have symmetry lines here, here, and here. So we already looked at this symmetry, this one, and then determined that this is H. No, this was ET is equal to 0, so this is spec. And then now, if we were to trace this and then see which plane has is 90 degrees offset from this, we have that it falls on this, which we have to look at what symmetry we have on this plane. So any of these two planes you take that are 90 degrees offset from each other, you see that it's always one of these and then one of these. So this is 90 degrees to each other. So we have to check the symmetry on the other plane. I hope I can clear this. Yes. Okay. That I think went well. First time using it. Okay. So now let's look at the symmetry on this other plane. So I go to field and then I rotate it a bit to this. Let's see. What was the problem? This is not rotating. Why? It should be free. Let's say Z. Okay, and then free. Let me make it to X. Okay. it's rotating again, and so yes, so let's see. Now we have that on this plane, we have that ET is clearly not 0. You could see the field, but then HT is 0. It's identically 0 on this plane. So we have that this condition is fulfilled. Now, if you were to check for a decapole for m is equal to 5, then you would also have similar condition. So we're going to apply this condition next. I think I should create a new file. I'll create a new file and then we would see. So I'm going to just copy this over and then put symmetry m odd. Yes. No, it's opening another window. I have to close it on this, save, and close. And then open it here. Yes, so remember what we are looking at is or what the symmetry conditions we are applying is YZ plane ET is equal to 0 and XZ plane HT is equal to 0. So if I should go to simulation background, so on one of the planes ET is equal to 0 and the other one X HT is equal to 0. So it could also be HT is equal to 0, ET is equal to 0. Okay, let's like this and then okay. So I calculate this, and then you see that we have the same reduction in the number of tetrahedrons once it's done meshing. Yeah, so 5,203. So this should also run pretty quickly and be done in a jiffy. Yes, and it's done. And what do we have? We have that now we wouldn't have any monopole modes at all and quadruple modes. So you can see that we have first the dipole mode, and that corresponds to this. So go to absolute value and reset scaling. Yes. So what do we have? Yes, so we have this, but then in the original case we had two polarizations, but then like I also mentioned in the previous video, you only have one polarization of this. Let's look at the frequency 1619 and let's look at the frequency 1619.04, but then the other one is 0.01, but then it's the same, it's the same mode, but then just one polarization. Then the next mode would be the second dipole mode, which is this 1793. And so the second dipole mode was 4, which is this 1793. So it's the same mode. Then the third mode was also a dipole, yes, at 2471 megahertz. So that should be 2471 megahertz. So it's giving just one polarization, while for the full model you have the two polarizations, which is the degenerate. So you have repeated eigenvalues in your solution, your eigenvalue problem solution. Yes. So then the next one is another dipole mode at 2579. So just one polarization still, and that's this 2579. So you see that you do not have any quadruple modes because quadruple modes do not satisfy this boundary condition. I think the last thing I'll check is and then the last one is your sextuple mode. Like I also mentioned, you see that you see the conditions, and then you see that now it is aligned to the two axes, and then you have these two. Yeah, although this one is not aligned, but then I'm applying the boundary condition fix, and then you only had to solve for just a quarter of it. Yes, so one last thing I would like to show is for the quadruple modes. Now I mentioned that we had two different boundary conditions. We could either apply two PEC or two PMC. So quadruple modes. So let's test that. And for this one, if I should run it, then I would not expect what I would not expect to see. I would not expect to see any monopole modes. I would also not expect to see any dipole modes. What I would expect to see is just quadruple modes. And I mean, in this frequency range, probably there are also some higher other modes that satisfy the same conditions as the quadruple modes, and then those ones would also appear. But then in this frequency range, we only have up to sextuple mode. So I'm expecting to see just quadruple modes in this run that I'm going to do now. So I'm going to change the symmetry conditions. What's going on now? The problem to mesh, but yeah, I don't care about that for now. So that's this, and then I run this, so I should have just the quadruple modes. It should be done anytime now. And yes, so like I said, let me look at the results first. Now I have just three modes. So the first one is a quadruple mode contour. It's a quadruple mode at 2298. Now just look at this. Remember, for this we had the monopole and the quadruple mode. So this is 2298. Then the second one is the second quadruple mode was at 2471. And then that's what we should have here, 2471. And then the third dipole mode should be at oh, this is monopole mode. So there's a third mode. Now let's see which mode this is. 2498. Let's see. Is this a monopole mode? It looks like a monopole mode. H. This looks like a monopole mode. So probably wait. Or is it non-physical? No, it's a physical mode. Yes, this is a monopole mode, and I suspect that this should be a TE mode. So for a TE mode, I think 2775. No, this is 2498. I think this should be present in the full geometry. Oh, we missed that. Yes, so this is a monopole mode and this is a TE monopole mode. Okay, now I go to make corrections again. And yeah, I mean, I usually like just have this at the back of my head, but I think this is the first time I'm really looking at the differences in all of these modes. So this is a TE. This is a TE01 mode. So what this means is that let's see, to make sure it's yes 2498, and let's see, yes, this is a TE mode. Here's a T01 mode. So and then that's what you have here. So what this should mean, the modification I'll be making to this is that for the HH you would have just the TM mode. So I was actually correct surprisingly, but then I didn't know that this was the case. I thought for all TM modes. So yes, so for I think then this should be for all TM modes, at least for the monopole modes. This is just for TM. Then if you should apply, let's see, monopole modes, TE modes, as TE0 NP modes, then the condition you want to apply is this. Yes. So this is the condition you want to apply. If you should apply this condition, then like we saw here, you wouldn't have the TE monopole modes, and I think you also would not have the TE quadruple modes. You could check that, and then if you have the TE quadruple modes, you could let me know in the comment. Should I check it? No, I'm going to stop it here. I hope to check it at my own free time because most of the time I usually don't deal with quadruple. I don't really look at quadruple. I only look at monopole and dipole modes. But then it was interesting to see that yeah, if you should apply your applying just the HT, the PMC, so tangential magnetic field 0, um, you would only have the TM zero. You only have the TM monopole modes, and also I think the TM quadrupole modes. And then when you apply electric field on both, so electric tangential electric equal to 0, then you now have the TE monopole modes. So yeah, it was interesting to see. If you have any questions or any observation, or maybe you spotted a mistake, please let me know in the comments. Yeah, I think that was it for this video. So you see, you could really reduce the computation time and also the number of modes that you are dealing with. um yeah, until another video. Bye.